The space, often depicted as the final frontier, evokes images of majestic galaxies, shimmering nebulae, and boundless opportunities for exploration. It captivates our imagination with the promise of adventure and discovery. However, while space may be enchanting and beautiful, it is also one of the most hostile and terrifying environments we can conceive. Beyond the allure of distant stars and the grandeur of cosmic phenomena lies a reality fraught with danger, unpredictability, and existential threats. As humans have ventured beyond the protective envelope of Earth's atmosphere, we have encountered a realm where the familiar rules of life no longer apply. The vacuum of space, the absence of gravity, and the relentless barrage of cosmic radiation present challenges that are both scientifically and existentially daunting. The harsh conditions of space, combined with the unpredictable nature of celestial phenomena, create a landscape of horror that contrasts sharply with the romanticized visions often portrayed in the media. In the year 1931, at Colchester, England, a historic town known for its Roman heritage and academic traditions, a boy growing up in this intellectually stimulating environment developed a fascination with mathematics and science early on, shaped by his father's influence as a mathematician. His pivotal contribution to space science emerged from his work on the theory of general relativity and black holes, particularly through the Penrose-Hawking singularity theorems. These groundbreaking theories have profoundly shaped our understanding of cosmic phenomena, including the nature of black holes and the universe's structure. His theories invite us to ponder the deeper structures of reality and the cosmic dance of creation and decay. He is known as Roger Penrose. For every breathtaking photograph of a nebula or every inspiring tale of interstellar missions, there is a hidden undercurrent of peril that threatens the very essence of human survival. Space is not just a vacuum of emptiness. It is a complex, dynamic environment where the smallest miscalculation or oversight can lead to catastrophic consequences. One of the most disturbing aspects of space is its sheer indifference to human life. In the void between planets and stars, there is no atmosphere to shield us from the harsh realities of the cosmos. The vacuum of space can tear apart our bodies, while the intense radiation can penetrate and destroy our cells. The absence of sound and the lack of immediate feedback make the dangers of space feel even more alien and inescapable. Despite the numerous scientific advancements and technological innovations that have allowed us to explore space, we are still woefully unprepared for many of the threats that lie beyond our home planet. The vast majority of space remain uncharted, and the risks associated with deep space exploration are often underestimated or misunderstood. The exploration of space is not only a quest for knowledge, but also a testament to human resilience and ingenuity in the face of overwhelming odds. As we continue to push the boundaries of space exploration, it is essential to acknowledge and address the terrifying aspects of the cosmos. By understanding the risks and preparing for the challenges, we can better appreciate the complexities of space and the true nature of our place within it. The universe is a vast, unforgiving realm, and our journey into the unknown requires both courage and caution. In this exploration of space's most terrifying aspects, we will uncover 9 uncommon and alarming facts that reveal the darker side of the cosmos. These facts highlight the myriad dangers that await beyond Earth's protective veil and underscore the importance of vigilance and preparation as we venture into the vast expanse of space. You're watching Space 9, unveiling the mysteries of the cosmos, your gateway to the universe. The vacuum of space, a harsh reality. It is one of the most inhospitable environments imaginable. In the absence of atmospheric pressure, humans would face immediate and devastating consequences. The lack of pressure causes bodily fluids to boil, including the water in your tissues. This would lead to severe swelling and potential rupture of tissues. Without the protection of a spacesuit, You would lose consciousness within seconds due to hypoxia, and death would follow shortly thereafter. The silent and airless nature of space only adds to the eerie sense of isolation and danger. In practical terms, the vacuum of space is not a perfect void. It contains sparse particles of gas, cosmic dust, and radiation. However, compared to the dense atmosphere of Earth, the vacuum of space is essentially empty. This emptiness is not just a lack of air, but an absence of the conditions necessary for sustaining life as we know it. In everyday experiences on Earth, we are accustomed to atmospheric pressure, the weight of the air pressing down on us. This pressure is a force exerted by the weight of air molecules and is crucial for various physiological processes. In space, however, the absence of atmospheric pressure means that the conditions are radically different, posing severe risks to human life and technology. Exposure to the vacuum of space can have catastrophic effects on the human body in a matter of seconds. Without the protective environment of a spacecraft or spacesuit, a person in space would face the following immediate dangers, such as boiling of bodily fluids. In the vacuum of space, the pressure is so low that the boiling point of liquids drops significantly. This means that the fluids in the human body, including saliva and blood, would begin to boil at body temperature. This process, known as ebulism, would lead to severe swelling and potential rupture of tissues. Decompression sickness. Rapid decompression in space can cause nitrogen dissolved in the blood to form bubbles, leading to decompression sickness, or the bends. This condition can cause joint pain, dizziness, and potentially fatal damage to tissues and organs. Hypoxia and asphyxiation. With no atmosphere, there is no oxygen to breathe. In the vacuum of space, a person would lose consciousness within 15 seconds due to hypoxia, as oxygen levels drop rapidly. This loss of consciousness is followed by asphyxiation, as the body's oxygen reserves are depleted. Temperature extremes. Space is also characterized by extreme temperature variations. Without an atmosphere to moderate temperature, a person exposed directly to the sun would experience temperatures soaring to 250 degrees Celsius, 120 degrees Celsius, while in the shadow, temperatures could plummet to 250 degrees Celsius, 157 Celsius. These extremes can cause severe thermal stress and damage. As we advance in space exploration, understanding and mitigating the effects of the vacuum of space will be crucial for future missions. With ambitions to explore Mars, establish lunar bases, and venture further into the cosmos. Addressing the challenges of the vacuum is essential. For example, enhanced spacecraft design. Future spacecraft will need to incorporate advanced materials and technologies to provide better protection against the vacuum's harsh conditions. Innovations in life support systems, radiation shielding, and thermal management will be critical for long-duration missions. Spacesuits will continue to evolve, incorporating new technologies to improve comfort, mobility, and protection. Developments in materials, science, and engineering will play a significant role in creating suits that can withstand the vacuum of space more effectively. Ongoing research into the effects of space exposure on the human body will help address the long-term health impacts of space travel. Understanding how to mitigate bone and muscle loss, manage fluid redistribution, and support mental health will be essential for successful missions. White holes. Theoretical, time reversed. When we explore the depths of theoretical physics, we encounter fascinating and often mind-bending concepts that challenge our understanding of the universe. Among these concepts are black holes, regions of space, where gravity is so intense that nothing can escape their grasp. Their existence has been confirmed through various observations and theoretical studies. However, their mysterious counterparts, white holes, remain purely theoretical and represent some of the most enigmatic and thought-provoking ideas in modern cosmology. White holes are a theoretical reverse of black holes. Instead of pulling everything in, white holes could be spewing matter out. While still hypothetical, their existence could mean there are places in the universe where matter is expelled into our reality in ways we can't comprehend. The consequences of encountering such an entity could be catastrophic. The concept of a white hole arises from solutions to Einstein's field equations in general relativity, which describe how matter and energy influence the curvature of space-time. The most famous solution is the Schwarzschild solution, which describes a non-rotating black hole. When the equations are extended to consider time reversal symmetry, where time is considered to run backward, white holes emerge as a theoretical possibility. The more we learn about space, the more it reminds us how small and fragile we are. Yet, exploring these mysteries is what makes us human. With each discovery, we learn, grow, and adapt, preparing ourselves for whatever the universe has in store. The theoretical foundation for white holes stems from the concept of time reversal symmetry. This symmetry suggests that physical laws should remain unchanged if time is reversed. For black holes, reversing time would transform the infall of matter into an outflow. White holes would thus be the time-reversed counterparts of black holes. Some key properties and theories related to white holes include no entry zone. Unlike black holes, which have an event horizon that traps everything, white holes would have an event horizon that prevents matter and energy from entering. This means that once matter is ejected, it cannot be drawn back in. Singularity at the core. Similar to black holes, white holes are thought to have a singularity at their core. This singularity would be a point where the density of matter is infinite and the known laws of physics cease to function normally. Possible connection to black holes. Some theories propose that white holes could be connected to black holes through wormholes. According to this idea, a black hole could serve as an entry point to a wormhole, with a white hole serving as the exit. Such a connection would allow matter to travel from one part of the universe to another, potentially offering a mechanism for matter and energy to be distributed across space. While the concept of white holes is intriguing, it faces several theoretical and observational challenges, such as lack of evidence. As of now, there is no observational evidence for the existence of white holes. Unlike black holes, which have been indirectly observed through their effects on nearby matter and the detection of gravitational waves, white holes remain purely theoretical constructs. Instability. Issues. White holes are predicted to be highly unstable. Any small perturbation could cause them to collapse or revert to a black hole-like state. This instability makes them difficult to study or detect, and raises questions about their practicality as real cosmic objects. Information paradox. The information paradox, a puzzle related to what happens to information that falls into a black hole, is also relevant to white holes. If white holes are connected to black holes via wormholes, it might provide a mechanism for information to be transferred across the universe. However, this raises complex questions about the preservation and retrieval of information in the universe. Hypernovae, even deadlier than supernovae. In the grand tapestry of the cosmos, supernovae are already among the most awe-inspiring and catastrophic events we can imagine. These stellar explosions signal the violent end of a star's life cycle, releasing immense amounts of energy and scattering heavy elements across the universe. However, there exists an even more catastrophic phenomenon in the cosmic arsenal: the hypernova. Hypernovae are essentially supernovae on steroids, exhibiting a level of energy and destructiveness that dwarfs their less violent counterparts. Understanding hypernovae reveals a new dimension of cosmic violence and danger, with implications that stretch beyond the confines of our planet. A hypernova is an exceptionally powerful type of supernova, characterized by an explosion that releases significantly more energy, about 100 times greater than that of a typical supernova. While supernovae occur at the end of a massive star's life, when it exhausts its nuclear fuel, hypernovae are associated with the collapse of extremely massive stars, or the merger of compact objects, such as neutron stars or black holes. The term hypernova is often used to describe the most energetic explosions known in the universe. Hypernovae can produce gamma-ray bursts, GRBs, which are among the most luminous and energetic events observed in the cosmos. These gamma-ray bursts are incredibly intense flashes of gamma radiation that can outshine an entire galaxy for a brief period. The sheer scale of energy released during a hypernova poses significant dangers, especially if such an event were to occur in proximity to Earth. The gamma radiation from a hypernova can be deadly. If a hypernova occurred within a few thousand light years of Earth, the radiation could have severe consequences for our planet's atmosphere and biosphere. Gamma rays are highly energetic and can penetrate Earth's atmosphere, potentially causing widespread damage to the ozone layer and increasing radiation levels at the surface. Atmospheric and biological impact. Increased gamma radiation would deplete the ozone layer, exposing the Earth's surface to harmful ultraviolet radiation from the sun. This could result in increased rates of skin cancer, damage to crops, and disruptions to ecosystems. The long-term effects could be catastrophic, leading to significant biological and environmental consequences. Potential extinction-level event. While hypernovae are incredibly rare, their potential to cause extinction-level events cannot be discounted. The release of massive amounts of energy and radiation could disrupt the climate and ecosystems, possibly leading to a mass extinction event if the effects were severe enough. Despite their destructive potential, hypernovae are incredibly rare. They are associated with the most massive stars and specific cosmic events, such as the mergers of neutron stars or black holes. The conditions required for a hypernova to occur are not common, which is why these events are relatively infrequent in the cosmic calendar. However, their rarity does not diminish their significance. Hypernovae are essential for understanding the extreme end of stellar evolution and the potential hazards they pose to life on Earth. The study of hypernovae also provides valuable insights into the processes that shape the universe and contribute to the formation of heavy elements. Hypernovae play a crucial role in the evolution of galaxies and the cosmos as a whole. As our observational capabilities and theoretical models advance, we continue to uncover the mysteries of hypernovae, revealing the sheer scale of violence and beauty that characterizes the universe. Tidal forces from exoplanets. Planets that orbit stars outside our solar system exhibit a remarkable diversity of conditions and characteristics. Some of these exoplanets are located so close to their parent stars that they experience extreme tidal forces. These tidal forces have profound effects on the exoplanet's geology and climate, creating conditions that are both fascinating and extraordinarily harsh. Among the most dramatic consequences of these tidal forces are intense volcanic activities that continuously reshape the surface of these worlds. Tidal forces arise from the gravitational interaction between two celestial bodies. When one body orbits another, the gravity exerted by the central body creates differential forces on the orbiting body. These forces stretch and distort the orbiting planet, leading to tidal effects. The magnitude of these tidal forces depends on several factors, including the distance between the two bodies, their masses, and their relative positions. On Earth, tidal forces from the Moon cause ocean tides, creating bulges of water that rise and fall. Similarly, in the case of exoplanets orbiting very close to their stars, the tidal forces can be immensely stronger, leading to dramatic effects on the planet's surface and internal structure. One of the most extreme examples of tidal forces acting on an exoplanet is seen in the class of planets known as hot Jupiters. These are gas giants that orbit their stars at incredibly close distances, often much closer than Mercury orbits the Sun. The intense tidal forces experienced by hot Jupiters are a direct result of their proximity to their parent stars. The tidal forces experienced by exoplanets, especially hot Jupiters, can lead to some of the most intense volcanic activities observed in the universe. For example, surface deformation. The constant stretching and squeezing of the planet's surface due to tidal forces can cause significant geological stress. This stress can lead to the formation of fissures, volcanic rifts, and active volcanic regions. The surface of such a planet may be in a state of near-continuous eruption, with lava flows and volcanic plumes constantly reshaping the landscape. Extreme temperatures. The tidal heating not only drives volcanic activity, but also leads to extremely high surface temperatures. On some exoplanets, these temperatures can be high enough to cause molten rock to flow freely on the surface, creating a planet-wide volcanic landscape. The intense heat also means that the planet's atmosphere, if it has one, could be thick with volcanic gases and ash. Atmospheric effects. The volcanic activity has a profound impact on the planet's atmosphere. Gases released from the volcanoes, such as sulfur dioxide and carbon dioxide, can contribute to a thick, greenhouse-like atmosphere. This atmospheric composition can trap heat, further increasing the surface temperature and contributing to a volatile climate. HD 2009-458b, OSIRIS, and WASP 112b are the examples of the exoplanets that provide concrete signs of how tidal forces lead to extreme volcanic activity. The exploration of exoplanets subjected to intense tidal forces and volcanic activity reveals a universe filled with extreme and dynamic environments. While these planets may seem inhospitable by Earth standards, they offer a glimpse into the diverse and extraordinary phenomena that characterize the cosmos. The study of these extreme worlds not only enhances our understanding of planetary science, but also inspires us to think about the boundless possibilities that exist beyond our solar system. As we continue to explore the far reaches of space, we gain valuable insights into the forces that shape planets and the incredible diversity of environments that populate our universe. The phantom zone, where planets get ejected. In the grand narrative of cosmic phenomena, few scenarios are as eerie and unsettling as the fate of planets ejected from their star systems. These planets, sometimes referred to as rogue planets, are cast adrift into the interstellar void, condemned to wander the darkness of space without a star to orbit. Their journey through the cosmos is a haunting one, an existence marked by isolation and, often, an unforgiving environment. The story of these wandering worlds unfolds through the lens of gravitational interactions, planetary dynamics, and the harsh realities of a starless existence. The process of planetary ejection is driven by complex gravitational interactions, often involving multiple celestial bodies. Several key mechanisms contribute to a planet being flung out of its star system, such as gravitational interactions. In multi-planet systems, gravitational interactions between planets can lead to complex dynamics. If two or more planets come close to each other, their mutual gravitational forces can result in a significant exchange of energy. This exchange can alter the orbits of the planets, potentially leading to one of them being ejected from the system. Stellar encounters. Close encounters with other stars or massive objects can also influence a planet's trajectory. When a star passes near a planetary system, its gravitational field can perturb the orbits of planets, sometimes leading to their ejection. This is particularly significant in dense star clusters, where such encounters are more frequent. Instabilities in young systems. In young planetary systems, gravitational interactions can be chaotic and unstable. The migration of giant planets or the formation of new planets can disrupt existing orbits, causing some planets to be ejected from the system. Once a planet is ejected from its star system, it enters a state of profound isolation that includes interstellar wanderers. Without the gravitational influence of a star, rogue planets drift through the interstellar medium, the vast, mostly empty spaces between stars. These planets no longer experience the warmth and light provided by their former stars. plunging into a cold, dark environment where temperatures can plummet to near absolute zero. Frozen worlds. The absence of stellar heat means that any atmosphere a rogue planet might have had is likely to freeze out, leaving the planet's surface cold and barren. If the planet once had liquid water, it would freeze into ice, rendering the surface a desolate and inhospitable wasteland. Lack of light. With no star to provide light, the surface of a rogue planet is shrouded in darkness. The planet's surface would be illuminated only by faint starlight or distant cosmic sources, making it a dim and shadowy realm. The absence of light also means that the planet lacks the energy needed for photosynthesis or any similar processes. However, detecting rogue planets and understanding their properties pose significant challenges: dimness and distance. Rogue planets are incredibly difficult to observe due to their faintness and the vast distances they travel. Without the light from a star, these planets do not emit significant amounts of radiation, making them hard to detect with conventional telescopes. Gravitational microlensing. One method used to detect rogue planets is gravitational microlensing, where the gravitational field of a planet bends and magnifies the light from a background star. This technique has been instrumental in identifying some rogue planets, though it provides only brief glimpses into their existence. Direct observations. Directly observing rogue planets is challenging due to their faintness. Advances in observational technology, such as next-generation space telescopes, may improve our ability to detect and study these wandering worlds in the future. The phenomenon of planetary ejection and the existence of rogue planets present a dramatic and haunting aspect of the cosmos. These planets, cast adrift into the interstellar void, embody a fate marked by isolation and desolation. As our understanding of these wandering worlds grows through advances in observational technology and theoretical research, we gain valuable insights into the dynamic processes that shape planetary systems and the vast, mysterious expanse of space. The study of rogue planets not only enhances our knowledge of the universe, but also evokes a sense of wonder at the extreme and often solitary journeys undertaken by celestial objects in the darkness of the cosmos. The potential of alien megastructures. Occasionally, astronomers detect unexplained dips in the brightness of stars. One hypothesis is the presence of alien megastructures, such as Dyson spheres, massive constructs built around stars to harvest their energy. While purely speculative, the idea that highly advanced alien civilizations could build such colossal structures raises the question of what other advanced technologies might exist in the universe, and whether they would be benign or hostile to us. Alien megastructures refer to hypothetical, large-scale engineering projects that could be constructed by advanced civilizations to capture or utilize the energy output of stars. Some of the most discussed types of alien megastructures include Dyson spheres. Named after physicist Freeman Dyson, a Dyson sphere is a theoretical structure that encircles a star to capture a significant portion of its energy output. This could take the form of a solid shell, a swarm of satellites, or a more practical Dyson swarm of individual solar collectors. The concept aims to provide an advanced civilization with vast amounts of energy, far beyond what is possible with planetary-scale energy sources. Dyson swarms and shells. Dyson swarms consist of numerous independent satellites or solar collectors orbiting a star in a distributed pattern. Dyson shells, on the other hand, propose a more ambitious idea of a solid, or nearly solid, shell encompassing a star. While Dyson swarms are theoretically feasible, Dyson shells are more speculative due to the engineering challenges involved. Niven rings. Another proposed structure is the Niven ring, a hypothetical ring world proposed by science fiction author Larry Niven. A Niven ring is a megastructure that encircles a star at a fixed distance, providing a habitable environment on its inner surface. It is akin to a large artificial planet with a stable orbit around the star. The detection of alien megastructures, particularly Dyson spheres or swarms, is challenging due to their immense scale and the limitations of current observational technology. However, astronomers have proposed several methods to identify such structures. Unexplained dips in stellar brightness. One of the primary methods for detecting potential alien megastructures is through observations of unexplained dips in the brightness of stars. When a large object, such as a Dyson sphere or swarm, transits in front of a star, it can cause a periodic or irregular dimming of the star's light. Such anomalies are often investigated to determine their cause, including the possibility of artificial structures. Excess infrared emission. Advanced megastructures that capture a star's energy would likely re-radiate some of that energy as infrared radiation. By analyzing the infrared signature of stars and comparing it to expected models, astronomers can look for excess infrared emission that could indicate the presence of a large-scale energy harvesting structure. Astrophysical anomalies. Other potential signs of alien megastructures include unusual variations in the star's luminosity, color, or spectral features. These anomalies might suggest the presence of massive structures or objects affecting the star's light in unexpected ways. The exploration of alien megastructures remains speculative, but offers intriguing possibilities for future research. Observational advances. As observational technology advances, such as with more powerful telescopes and space missions, we may improve our ability to detect and study potential alien megastructures. Future research could provide more concrete evidence or refine our understanding of the conditions needed to construct such structures. Theoretical developments. Continued theoretical research into the feasibility and implications of alien megastructures can help refine our models and predictions. Understanding the limitations and possibilities of such structures can provide insights into the potential for discovering advanced extraterrestrial civilizations. SETI initiatives. The search for alien megastructures can complement existing SETI initiatives. By broadening the scope of our search and incorporating new methods, we can enhance our chances of discovering evidence of advanced life and understanding the broader context of extraterrestrial intelligence. The concept of alien megastructures represents one of the most fascinating and speculative aspects of the search for extraterrestrial intelligence. While the idea remains largely theoretical, it prompts profound questions about the capabilities and intentions of advanced civilizations. As we continue to explore the universe and develop new technologies, the possibility of detecting and understanding these colossal constructs offers a unique perspective on the nature of cosmic civilizations and their potential impact on our understanding of the universe. Quantum fluctuations. Reality's fragile foundation. Quantum physics suggests that reality as we know it could be far less stable than it appears. Quantum fluctuations can cause brief, spontaneous changes in energy that could theoretically lead to catastrophic events, such as the spontaneous creation of black holes or even vacuum decay, as mentioned earlier. While these events are exceedingly rare and unlikely, they highlight the precarious nature of our universe's foundational laws. While quantum fluctuations are a natural and integral part of the quantum world, they also hint at the potentially fragile and unstable nature of reality itself. This exploration into quantum fluctuations sheds light on the delicate balance of the universe and the profound implications for our understanding of existence. Quantum fluctuations arise from the uncertainty principle, which asserts that certain pairs of physical properties, like position and momentum, cannot be simultaneously measured with arbitrary precision. This principle implies that at the quantum level, energy levels are not fixed, but subject to fluctuations. These fluctuations manifest as brief, spontaneous changes in energy within a vacuum, leading to the temporary creation and annihilation of particles and antiparticles. Zero-point energy. Even in a perfect vacuum, where no particles are present, there exists zero-point energy, the baseline energy level that cannot be reduced to zero due to quantum fluctuations. This energy leads to the continuous appearance and disappearance of virtual particles, which are temporary entities that exist for fleeting moments before annihilating each other. Vacuum fluctuations. Quantum field theory posits that the vacuum is not an empty void, but rather a seething cauldron of fluctuating energy. These vacuum fluctuations can give rise to transient particle-antiparticle pairs that momentarily affect the energy of the vacuum before vanishing. The transient nature of quantum fluctuations introduces intriguing, if unsettling, theoretical scenarios that could have profound implications for the stability of our universe. Spontaneous black hole creation. Quantum fluctuations can, in theory, lead to the formation of microscopic black holes. In regions of space where energy densities become exceptionally high due to fluctuations, the gravitational field could potentially become strong enough to cause local space-time curvature, resulting in the creation of a black hole. Although such events are highly speculative and unlikely due to the extreme conditions required, they highlight the extraordinary potential consequences of quantum fluctuations. Vacuum decay. Another catastrophic event associated with quantum fluctuations is vacuum decay. This phenomenon involves a transition from our universe's current false vacuum state to a more stable, true vacuum state. If such a transition were to occur, it could lead to a catastrophic collapse of space-time, altering the fundamental constants of nature and potentially rendering the universe uninhabitable. Vacuum decay, while theoretically possible, is considered exceedingly rare and highly unlikely to occur in the observable universe. False vacuum instability. The concept of a false vacuum refers to a metastable state that appears stable but is not the lowest possible energy state. Quantum fluctuations could trigger a transition to a true vacuum state, causing the false vacuum to decay. Such an event would release an immense amount of energy and fundamentally alter the properties of the universe, leading to potentially disastrous consequences. The impact of quantum fluctuations on reality is closely tied to the principles of observation and measurement. Quantum entanglement. Quantum fluctuations also play a role in quantum entanglement, a phenomenon where particles become correlated in such a way that the state of one particle instantaneously affects the state of another, regardless of the distance between them. Entanglement challenges classical notions of locality and causality, revealing the interconnectedness of quantum systems. Observer effect. In quantum mechanics, the act of observation can influence the outcome of quantum events. This observer effect suggests that the measurement process plays a role in determining the state of a quantum system, further complicating our understanding of reality at the quantum level. Quantum fluctuations reveal a universe that is far more intricate and unstable than our everyday experiences suggest. These fleeting variations in energy highlight the fragile and probabilistic nature of reality at the quantum level. As we continue to explore the quantum realm, we gain deeper insights into the foundational principles of reality and the delicate balance that governs the universe. The unknowns beyond the observable universe. The observable universe represents the farthest reaches of the cosmos we can currently see, constrained by the finite speed of light and the age of the universe. Beyond this observable horizon lies the unobservable universe, an expanse of space that remains shrouded in mystery and speculation. While our observational tools and theories have expanded our understanding of the cosmos, they are limited by the boundaries of what we can detect. This veil of the unknown beyond the observable universe hints at potentially staggering and unsettling phenomena, stretching our comprehension of reality and survival. The observable universe extends approximately 13.8 billion light-years from Earth, defined by the distance light has traveled since the Big Bang. This boundary is not a physical edge, but rather a limit imposed by the finite speed of light and the expansion of the universe. Cosmic microwave background. The farthest we can observe is the cosmic microwave background, CMB, the afterglow of the Big Bang. This relic radiation provides a snapshot of the universe roughly 380,000 years after its inception, offering clues about its early conditions. Expansion and the observable limit. The universe has been expanding since the Big Bang, meaning that regions of space that were once within our observable reach have since moved beyond it. The expansion rate, governed by dark energy, is accelerating, further distancing us from the edges of the observable universe. Beyond the observable universe lies a region that remains fundamentally inaccessible to us. This unobservable universe may contain a wealth of unknown forces, galaxies, and structures. It is conceivable that beyond our observational limits lie entire galaxies or clusters of galaxies that we are unable to detect. These regions could harbor cosmic structures vastly different from those we observe, potentially influencing the broader dynamics of the universe. Exotic matter and energy. The unobservable universe may contain forms of matter and energy beyond the known types, such as dark matter and dark energy. While dark matter and dark energy are theorized to exist based on their gravitational effects, their precise nature remains unknown. Unseen forces and phenomena. The unobservable universe could harbor forces or phenomena that challenge our current understanding of physics. For instance, there might be new types of fundamental forces or interactions that could radically alter our comprehension of the universe's laws. The very existence of an unobservable universe implies that there could be cosmic-scale threats lurking beyond our detection. Astrophysical hazards. The potential presence of previously unknown astrophysical phenomena, such as rogue black holes or massive energy fluctuations, could pose unforeseen dangers. For instance, a large undetected cosmic event, such as a supernova or gamma-ray burst, could have far-reaching effects if it were to occur in the vicinity of our observable universe. Interaction with the unobservable universe. The unobservable universe might interact with the observable one in ways we cannot currently predict. For example, fluctuations in dark energy or unknown forms of matter could influence the expansion rate of the universe, potentially leading to catastrophic changes in its structure. The multiverse hypothesis. Some theories suggest that our universe might be just one of many in a larger multiverse. If this hypothesis is correct, interactions or collisions between different universes could result in significant and potentially dangerous effects on our own universe. The unobservable universe, constrained by the limits of our current observational capabilities, harbors potential phenomena and threats that challenge our understanding of reality. While we may never fully penetrate this cosmic frontier, the quest for knowledge continues to push the boundaries of what we know. The cold death of the universe. The concept of the heat death of the universe describes a scenario in which the universe reaches a state of maximum entropy, where all energy is evenly distributed and no thermodynamic work can be performed. In this scenario, stars burn out, galaxies drift apart, and the universe becomes a cold, dark expanse. This eventual fate, predicted to occur billions of years in the future, represents a chilling end to the dynamic and vibrant universe we know today. The heat death of the universe underscores the impermanence of cosmic phenomena and the inevitable decline of cosmic structures over time. Entropy, in thermodynamics, measures the amount of disorder or randomness in a system. As entropy increases, the system becomes more disordered and less capable of performing work. The heat death scenario arises from the second law of thermodynamics, which states that the entropy of an isolated system always tends to increase over time. Thermodynamic equilibrium. The heat death of the universe describes a state of thermodynamic equilibrium where all energy is evenly distributed throughout space. In this state, there are no temperature gradients or energy differences to drive physical processes or perform work. The universe reaches a state of maximum entropy, and all energy becomes uniformly spread out. Cosmic expansion and entropy. As the universe expands, the distribution of energy and matter becomes more uniform. Over time, galaxies will move farther apart, stars will exhaust their nuclear fuel, and the universe will evolve toward an increasingly uniform state with high entropy. The heat death of the universe is predicted to occur billions to trillions of years in the future, on a timescale that far exceeds the current age of the universe, which is approximately 13.8 billion years. As the universe progresses toward its heat death, it will become increasingly cold and dark, stellar evolution. Stars will burn out over the course of billions of years. Initially, they will exhaust their hydrogen fuel, leading to the formation of white dwarfs, neutron stars, or black holes. As stars die and no new stars form, the universe will gradually become darker. Galactic evolution. Galaxies will continue to drift apart due to the expansion of the universe. The interactions between galaxies will become increasingly rare, and the space between them will grow vast and empty. Black hole era. Over even longer timescales, black holes will dominate the universe. They will gradually